Hello, welcome to Pre-AP Algebra 2 and AP Stats YouTube channel. Before you start, can you smash that like button, give it a nice like, and then be sure to subscribe, join the Bell Squad, please turn on notifications, and I'm giving away a free nickel to the first person who subscribes today.
So you heard right, this is the final unit of AP Statistics. I know everyone is so excited. So this is, half of it is a review from the linear regression unit, which I think, if I can recall, was unit 3, and we are learning new parts to that. So whenever we're creating scatter plots and we're analyzing data, what kind of data do we have? Bivariate. Perfect. So we make scatter plots and we analyze that. And the big phrase from unit 3 that we said all the time was that correlation does not imply causation. Perfect. Now, when we will now run an inference test, so we'll be doing confidence intervals, hypothesis tests, and sampling distributions on bivariate data. So everything we've done up until this point has only been with one variable, univariate. Now we have bivariate. Yes. So suppose we were to investigate the relationship between the first year college grade point average and high school grade point average. So do you think that they have a correlation? Like how well you did in high school, does that determine or does that predict how well you're going to do your freshman year of college? It could. So is the first year college grade determined solely by your high school GPA? It's like, is that the only determining factor? Definitely not.
Definitely yes.
And so a relationship in which the value of y is completely determined by x is called a deterministic relationship. And that would be when your r squared value, that coefficient of determination, is 100%. So do you remember kind of talking about r squared? And the script for r squared is the percent of variation in y can be explained by the relationship between x and y. Perfect. And so, like, if this were 100% or 1, then I guess it would be, well, we normally write it in a percentage. So if it were 100%, that would mean 100% of your GPA in college is determined or predicted from your high school GPA. And that never ever happens because there will always be outside factors that can play a role into your y value. Not just, so it's kind of like your weight and your height. So your weight is not going to be solely predicted by your height. There's other factors that play into your weight as well. But if that were to happen, then we would call that a deterministic relationship. So that's just a vocab term to know. Does not ever happen.
It doesn't? Oh.
No. So a description of the relationship between the two variables are not deterministically related. They can be given by a probabilistic model. So this essentially is our function. So y equals f of x plus the error, or how much it deviates from the predicted value. So we would call this our error. The deterministic function of x is just our a plus bx. So that's what this is. So this is the formula that we're used to knowing, we learned so far. But now we're going to refer to this e as an error variable. And the error is the same thing as your residual, just how far away you are from your predicted value. So we call that, we're going to refer to that as error now. We didn't know the word error back when, that was like what, September? We didn't know what that meant. Now we are mature enough to handle this word. Error. Yes. We are now mature enough to handle this word. Exactly. This formula right here is what we call the population regression line, where we're using alpha, beta to represent the population, y-intercept, and the population slope. They are population because they are Greek variables. Yep.
So on the last slide, were you saying that fx is the same as like bx?
A plus bx.
Oh, all of that goes into fx.
It's like your predicted regression line. Without any error, then all of your values would fall exactly on the population regression line. So like if you had no residuals or 0 residuals, then everything would be on the line. So once again, errors are the same thing as residuals. What's another name? We just said that, residuals. So let's look at the heights and weights of a population of adult women. So we took I guess this is a population where every single woman in the population is 60 inches tall. So
That's not random.
no, but it's a population.
That's evidence of design.
I mean, you don't ask a woman.
Intelligent design.
What population would this be? Like a
In Nepal,
A-
Nepal, everyone is like 5 foot.
small population.
Female pilots.
No, it's
Female pilots are all 5 foot
Gymnasts.
tall.
Yes.
Exactly.
No, it's from UTD.
Gymnasts from Ukraine.
Gymnast. Where did that come from?
I don't know. A very small part of Ukraine, like the northeastern district.
What if a
Yes.
Ukrainian watches this in Kiev?
And how many people are in this population? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay.
Shout out to all the Ukrainians.
Okay. So weights of these women will vary, but the heights are all the same. And so if we find the mean, it's going to be somewhere around the center. And then we have error values. What would the sum of these error values equal? 0, because the sum, yes, the sum of the residuals, the sum of the errors is always equal to 0. Always, always. So remember that. Now, when we're doing a write-up, so a confidence interval or a hypothesis test, I'm going to show you the assumptions, but they look a lot lengthier on this slide, then we will kind of like shortcut them once we do a full write-up. So I'm just going to talk about them really quickly. So the first assumption is basically that the mean of all of your errors is equal to 0. So if you were to add up and average all of your errors, they would always be 0. So that's just something that you check. And I'll show you how we're going to check that in a minute by making a graph.
So for this one, we can just say the mean of errors is 0.
Yes. The second assumption is that your observations are independent. So like basically your sample is random and independent of each other.
Random independent sample. Samples or sample?
Sample. And the distribution of your errors are normally distributed. So basically all of your data points are normal. That's always been an assumption, that we have a normal distribution.
How do we know that based on this graph?
We're going to create graphs from this. So you will have graphical evidence for each one of these assumptions. And notice that each one of these assumptions is talking about the errors or the deviations. So that's kind of like the main key point of these assumptions, is that we're talking about the errors, and that essentially just means that we're talking about each individual observation. We're just referring to them as errors. So all of the observed values are technically errors because they don't fall on the line of best fit or the least squares regression line. So imagine we kept going and we took a new so we have a new population, and maybe these are just women in the
Ukraine.
Ukraine, yes. Where would you expect the population regression to be? They would go through the mean of all of my individual x values. So they're going to go through each mean. So essentially we want the standard deviations of all these normal distributions to be the same. So fourth assumption is that the standard deviation of the errors is the same. Now, this is really hefty and it's a lot of text. So whenever we do a write-up next class, we will kind of shorthand it into it being a little bit more simple. And these assumptions are really the main part of the write-up. So here's a little 3D graph for us. Imagine each one of these x values represents a different height. And then the y values, so kind of shooting up, are the frequency of the weights. So the outliers are going to be, like if your height is 5 feet, there's going to be outliers at really large weights and really small weights, but most of the weights are going to be clustered in the middle. So does everyone kind of understand how this graph is represented? Like there's a high frequency at the average weights. So when a woman is 5 foot tall, more women are going to weigh around, like, I don't know, 110 or something.
Like 90, be safe.
And less women will probably weigh 80 and 160, something like. I literally just made these up.
Wow.
I just made them up, okay?
That's a large win.
I'm just saying.
How can it be normal for 1 in 30?
To all those large women out there, give us a like.
140, okay? 140. Y'all stop yelling at me.
Can we do 100?
No. I just made that. All I'm trying to say here is that you have a higher frequency at the average and a lower frequency at the end points.
All large.
So every x value is a normal distribution. That's all I want you to get.
All large women, please subscribe.
Hit that like button.
Smash that like button.
Smash that like button.
Smash that like button.
Subscribe if you like our content to see more.
Oh my.
Read 10,000
And
likes next
the
video
standard
video.
deviation is the same for each x value. So, if you want to see all of the assumptions come to life, just study this 3D plot right here.
And also smash that like button.
Wait, how is the standard deviation the same for all of them?
Every x value, so each one of these normal curves has the same standard deviation. Like each one of these x values has the same standard deviation.
How does one get a sample that just happens to have exactly the same?
It's not a sample, it's a population.
looks a little skewed to me.
Can you ever do this then? Like unless it's super rare cases.
No, you can always do this. It always works out that way.
But how do you make the standard deviation the same?
Okay, now we take a sample. We take a sample and we use the y hat equals a plus bx. Now this is not a population, this is a sample. And how do we know it's a sample versus a population?
No Greek.
The hat and no Greek.
No what?
No Greek. No Greek letters. So A is the point estimate of alpha, which is your y-intercept, and B is the point estimate of beta, which is your slope. So sample slope, sample y-intercept.
Whoa, that formula.
Wow.
These are different B and alphas, right?
Mhm. So when you are interpreting this, so if I said, like, what is the, if I said plug in an x value, so plug in x equals 60 inches tall. When you plug that in to your y hat equals a plus bx, you're predicting two things, or you can interpret this in two different ways. And I will ask you to interpret it both ways. So one interpretation is that a woman who is 60 inches will potentially, or I predict that they will weigh 110 pounds. So it's for an individual. So the next woman that walks through the door that's 60 inches tall, I predict that one person will weigh 110 pounds. So that's for that one person. The second interpretation is that the average for all, so the average for all 60-inch tall women weigh 110. So it's a prediction for the masses, and it's a prediction for that one individual person, because it's the only number that we can really use to predict. So for one person and the average for all people. Those are the two interpretations. So let's examine the sampling distribution of the slope, because remember each unit starts out with sampling distribution, confidence interval, and hypothesis test.
And just get the whole page, we're on page 209 now.
This next
Oh,
example
interesting.
is a little controversial too, Miss Ono.
Oh no.
It's about adolescents who are pregnant.
Oh my.
Birth weights.
Okay, so here we have
Oh, baby, you just get the like.
Here we have this formula. So weight equals negative 39.42 plus 2.5 height. What is the true slope of the regression line? Like if I had a question that said, what is the true slope? Well, what symbol would I use first of all if I'm saying the word true
Oh,
slope?
it's the population one, right?
Which is,
Y hat.
no, slope.
Just one. Oh, slope.
Slope is
B.
B, so
Beta.
beta. And what's the slope in this problem? Which number?
2.5.
2.5.
2.85.
Perfect. So beta is 2.85. Gonna skip that.
So true is about.
True is about the population. So
Oh my gosh.
What a tricky question.
here are the same assumptions for sampling distribution, confidence interval, and hypothesis test all have the same assumptions, all of them. You do not need to know this formula ever. You can just cross it out.
Even if we're doing it by hand.
You won't be doing it by hand.
Reese goes above me on.
Hey, what if your calculator is missing? You're straight on the island.
What's your calculator? Is it TI?
My calculator actually is missing.
What if you're using an Inspire and you can't do it? Right?
You're on an island and there are no power sockets. You're gonna be screwed.
You have to solve this math.
So the mean is equal to your slope.
What if you have only inspired a little bit
Well, then you have to get anywhere.
Now, the standard deviation, now listen, right here. This B, this little sub B, is talking about your, so when you're talking about a sampling distribution of B, you're essentially doing the sampling distribution of the slope. So every sampling distribution that we've done, whether it's proportion, mean, or now we're doing linear regression, they're always equal to the population. So like the mean of my p hat was p, mean of my x bar was mu, now it's beta. So essentially it's just the population. The standard deviation, you'll either have a list of data where you'll put it in, like you'll run a 1 var or 2 var stats and it'll give you the standard deviation, or it will be given in computer output. So that's why I said you don't need to know this formula. So you'll either have data where you'll do it in the calculator, or it'll be given in the computer output. Here is a graph where all of the heights are the same, and then here's a distribution of the weights. So here's just a scatter plot.
186.
Oh, that's larger than me.
So heavy.
So what distribution does their weight have? How could I tell? This is a
Linear.
normal probability plot.
Linear, which means
Approximately normal. And we're gonna make these, but it's approximately normal.
That person must have diabetes.
For all those diabetics out there, hit the like button.
Josh.
Okay. So what I want us to do right now is go ahead and put your X values in list 1 and your Y values in list 2. So medical researchers have noted that adolescent females are much more likely to deliver low birth weight babies than are adult females. Because low birth weight babies have higher mortality rates, a number of studies have been examined.
We're not in the notes anymore.
No, go ahead.
All Inspire users, leave a comment.
Okay, if I were to interpret the slope, what this would be, and remember you have to have these interpretations memorized for this test and for life from now on. So basically the weight, so your Y value increases 245.15 grams for each increase in one X value. So for every year that a mother's age is increasing, the baby's weight increases by 245.15 grams.
For each increase in blank.
What is the point estimate for the mean weight of babies born to 18-year-old mothers? So point estimate, that word, is basically just an estimation, plugging in 18 for X.
5,576. Oh, what the?
3,249.25.
2,000 here, 6,000.
So this is an estimate for the mean weight for all babies born to 18-year-old mothers. What's the second interpretation? So all 18-year-old mothers, and what's the second interpretation?
Individual.
That individual, a single baby born to 18-year-old mothers. Minus 1160. So two interpretations, mean for all and just one individual. This is the formula for variance. You do not have to have this memorized. You don't have to have this memorized. You can just cross it out. I don't know why it's all in there.
Let's just cross it out. The whole slide.
We would read this though as something good to, I guess, mention is when you see S sub E, that's the standard deviation of the errors. And because your subscript is E. And lastly, this right here indicates degrees of freedom. So my degrees of freedom for this unit is N minus 2. Why is this different than N minus 1?
Because now
You subtracted by one more than N minus.
One, I know, but can anyone think of a reason why that's the case?
Let's see.
What's the difference between all the past units and now this unit?
Univariate and bivariate.
Univariate and bivariate. So not the number of samples, but the number of variables.
Oh.
So if I only have one variable, I'm only subtracting 1.
Oh.
But, so we said it's N minus 2 because we have bivariate data. So we have to reduce the sample size by 2 because now we have 2 variables to deal with. Recall the coefficient of determination, R squared. We already kind of talked about that, the proportion of observed Y variation attributed to the LSRL between X and Y.
It's kind of jumping.
Yeah, I'm very.
I'm getting so disoriented.
Just slide right next to
Sorry.
it. 628.
it is.
Literally no good.
We just need
Yes. So here, I told you you won't ever have to do this by hand, so you can just, ignore all of that. But let's say that you are given this number right here, or the calculator gives you, and I'm going to show you how the calculator gives it in a minute. So let's say that the standard deviation of the errors is this. We do have a new interpretation. You can either add it in your interpretation page, or you can put it somewhere maybe at the bottom of this page. But if I were to interpret this number, I would say for a particular X value, so mother's age, this is just my X in context, the typical deviation for Y in context is whatever your standard deviation of the errors is. So this is a new interpretation or a new script that you are adding into your list. So the ones you should have memorized, you can write this out to the side. You should have slope, y-intercept, r squared, and I think we just added standard deviation of errors. Are there any more? Don't think so. So you should have these interpretations, or these scripts memorized. So here's r squared, approximately r squared percent of the variability in y can be explained by the LSRL, by this model. We're gonna skip this and do the write-up next time. I'm gonna show you all of the calculations, and then we'll do a write-up next class. So I just wanna show you kind of how to do it all on the calculator, and then we'll do the full stuff next class. So, confidence intervals, this is the formula. B, which is our sample slope, plus or minus, T critical value, which is T star, standard deviation of the slope. Do what? Right. And now our degrees of freedom is n minus 2. So we'll use inverse T, halfway to 100, and then degrees of freedom, which will be n minus 2 now. Let's see. I don't know if I want to put in new data.
I think we're good to call it a day.
No, we're not going to call it a day. Okay, so what I want us to do with our data that we have from our calculator, which is already in there, it is a stat test, and it is ln reg t interval, so it's option G. This is a linear regression t interval. So that is the name of this test. Let's use a 90% confidence level just for fun.
And then frequency is 1.
Frequency is 1.
Stat test?
Or reg
Stat
G.
test? Stat test?
Stat test G.
Stat test G.
Lots of
So when you do this, it gives you everything,
Is that S?
which is kind of nice. Yep. So here it gives you,
On my stat test, I'm a fool.
You fool.
so what it has given you so far is it gives you your interval, which you should get 159.78, 330.52. It gives you your sample slope, which is 245.15. Gives you your degrees of freedom. It gives you your S. This is your S, like the standard deviation of your slope, because that's the one that's in the formula. Then it also gives you your, if you were to do a predicted, like y hat, gives you your a value. Or b. So it gives you all of that information. It also gives you your r and your r squared. I will say these types of problems don't come up very often. They normally will give it to you in a computer output, but sometimes they do require you to do it on the calculator. So there's two ways to present bivariate data: through a list, like 2 lists, or through computer output. Mm-hmm. So I'm skipping this part. So here's the computer output. This is a completely new problem. So this is the second way that I could present data to you. Now remember or recall, the top is the regression equation line. Sometimes it's given to you and sometimes it is not. The number that is next to the word constant is always your what? Y-intercept. And then the number next to your x variable is your slope. Good. So treadmill is my x variable. I don't know what it's talking about in the problem, but that's always my x. This is my slope. Y-intercept. I would go ahead and label this if I were you. Now, the number we used to cross off everything. Now, we're going to keep this number. So look at the 0.5911. That is now my standard deviation of the slope, SB. So we're now going to keep this number.
Which one was A?
Top. A, B, S, B. We do not need this number.
Do you ever need the adjusting R squared?
Nope. And we don't need these either.
What is it? What is S?
Standard deviation of errors?
Standard deviation of the slope. Oh, this S right here? Yeah, this is standard deviation of the errors. This is my R squared. My degrees of freedom, I use the one next to the word residual error. And then I get rid of the rest of the stuff. And sometimes you'll be asked questions like, what is my sample size? Just looking at this computer output. How could I work backwards to figure that out?
What is the formula for
9 plus 2.
So my sample size would be 11. That's always kind of like a tricky question.
So wait, what did we do?
We just added 2
Two.
to 9. Now, these numbers right here are sometimes there and sometimes not, which is unfortunate when they're not, but you can always calculate them. This right here, this negative 3.95, would be my test statistic.
Oh my god. That's the p-value, ain't it?
Mm-hmm. And this is my p-value.
This is wild.
Now, something interesting about the p-value is it always does the p-value for a not equal to test. It only gives you that. So if you wanted to do a p-value for like a less than or greater than, what would you need to do?
Divide or multiply by 2? I don't.
Divide by 2. So if it's a less than or greater than, you want to divide it by 2.
I'm sorry, I missed all that.
So the p-value, if it is given, because this is all, I'm going to put a little asterisk next to it, because a lot of times computer output doesn't even give you those. You have to calculate them yourself. But if it does give it to you, the number under the t is your test statistic, and then the number under p is your p-value, but it's only your p-value for a not equal to test.
Oh.
And the reason why is because not equal to tests are the most common in this unit. Yes.
The most broad.
Why would they give us everything else if we don't need that? Or is that stuff you need for doing it by hand?
Is this when you would do it by hand?
You need
So,
all that to do it by hand?
mhm.
Oh, that's...
And so, if I were doing a confidence interval by hand,
Oh, Mark.
what is the formula?
B
Plus or minus T star
critical value
SB.
times the standard deviation of the slope.
And so I would take this number, negative 2.3335,
Oh.
plus or minus, I don't know what T star is, I'm going to figure that out in a second, 0.5911.
Wait, is the test statistic... Oh, wait, no, that's not the critical value.
No, that's not the critical value.
Oh. So the test statistic is...
So what confidence level do we want to use? 90? So if I did 90,
No, we're not... Oh.
to get my test statistic, I would have to do inverse T of 0.95, comma, what for degrees of freedom?
9.
9.
Why isn't it negative 3.99?
Because test statistics are when you're doing a hypothesis test.
Oh. Inverse T?
And so you end up getting 1.833. So when you have computer output, you have to do the confidence interval and the hypothesis test by hand. So you do need to have the formulas memorized.
Embedded in the long term.
Yes. And then you would actually do this using your calculator and you would get two numbers. So we did that by hand.
Yay.
How do we find this T star? I guess they did a 95% confidence level instead of 90. Oh well. Okay, and then hypothesis test. So the null hypothesis is always B or beta equals your hypothesized value. In this unit, it will always be 0. And then 0, 0. I guess I didn't click it enough. 0. And then this is the formula. So 0. So basically what you're saying, like if I were to interpret this, like if I'm talking about height and weight, I want your eyes on me because this is important. Because a lot of people don't understand why we do a hypothesis test. So the null hypothesis is that there is no linear relationship at all. And that, like when you have a slope of 0, so when your scatter plot looks like this, and it's just super scattered, and you have height and weight, the people are saying there's no linear relationship, but you think there is. So your alternative hypothesis, what you're trying to prove, is that there's either a positive relationship, a negative, or just a linear relationship in general. And that would mean that the slope, so the null is that there's no relationship at all, no linear relationship, but you're proving them wrong. So you're proving that there is a linear relationship. The formula is B, or slope, minus hypothesized value, which we always said is 0, divided by SB. So you can just memorize B over SB. The same assumptions, remember we're going to do that next class. So this is kind of what I was just explaining. If the slope is 0, there's no linear relationship. test statistic, p-value. And the p-value is always for a not equal to test. So just to say that again. Now, if I have this computer output, if I don't have these values right here, like if they're not given, and God has not blessed you, then you have to calculate it yourself. So T equals B over SB. Now, which number was my slope?
Negative 2.33.
So negative 2.3335. And remember that you keep all of the decimals in computer output. So if it went out 10 decimal places, you would keep all of them. And then what was my standard deviation of?
0.5.
So they're always side by side, so it's pretty easy to remember. And then you should get negative 3.95.
So how do you get the p-value from that?
Then, how do I get the p-value from that? That's a great question.
TCDF.
TCDF.
Hey.
It's a negative, so that means it's going to go to negative or positive infinity. Negative infinity, negative 3.95, and I have 9 degrees of freedom. But that just gives me a less than p-value. If I wanted a not equal to p-value, what would I need to do? Times it by 2. And that's how I would get the 0.03. 0.003. If it's a not equal to. So let's just kind of recap today, because this is all of it, and we're going to do write-ups next class. Let's just recap what we have. Okay, so go back to sampling distributions. We had that the mean of beta was equal to what?
Zero.
Just this for sampling distributions. So it's always equal to your population slope, which is what?
Mean equals P.
Beta. In this chapter, it's beta. And my standard deviation, what was that? Yeah. It was SB, right? Let me go back and look. It was sigma of beta, and that will usually be given to you. It's the sigma of the errors over the square root of SXX, but I said you don't have to have that memorized. So that will always be given to you. We don't do a whole lot of sampling distribution stuff in here. Confidence intervals. Now, if there's 2 ways you're going to be doing these. You'll either be given the data, in which case you would do stat test G, and that's a linear regression T interval. Or you'll be given the computer output, in which case the formula is B plus or minus T star SB. And degrees of freedom is always n minus 2. And then lastly, hypothesis test. If you're given data, we didn't even do this, but it would be stat test, let me see, F, and this is called a linear regression T test. And the formula for that is T equals B over SB. So that is it for today. I know it's a lot of information, but we'll go back and kind of do the write-ups next class. Yes. Yes.